Okay guys, let's look at today's lesson. We're looking at power series. We've talked about that definition before. Let's just talk about that again. The Maclaurin and Taylor series that we're working with, they are different from the series that we had in the last unit because they don't just have like an n and a number, they have x, a variable x. And so that is what makes it a power series. This is an example here of an infinite series and power series. Notice that it's centered at x equals 5, and each term of the series has a power of x minus 5, and so that's where it gets its name, power series. We have a definition here. This is just the definition of a power series, kind of writes it out there for you, what it takes to be a power series. To find the domain, basically the domain of f is the set of all x for which the power series converges. Alright, so this topic is a big deal, convergence of power series. It is on every AP exam I can remember. It will be on the AP exam. So we're going to spend today learning how to do that, learning how to find the radius of convergence and the interval of convergence. So let's talk about that. For a power series centered at C, there are 3 possibilities. Now that's kind of comforting. There's only one of 3 things that's going to happen. That's it. Either, number 1, the series converges only at the center, only at C. That's a possibility, where it only converges for one number. Number 2, the second possibility is that it converges for a specific interval of numbers, like 2 to 9 maybe, something like that. It converges for a specific interval. And the third option is that it converges for every real number, for all real numbers. And what we have are, I have 3 examples, one of each different type that we're going to work through. The one, I will just tell you, I'm doing this one first, the second one. Letting you know just so that you understand, that one involves, it's the most rigorous, it involves the most work to be able to look at that. So once you see the first example that I'm going to do, just understand that that one involves a second part that the other 2 don't. So there's actually 2 parts of work that we do when it converges to an interval. These 2 just require one part of work. Alright, so let's talk about what a radius of convergence is. So they usually represent it with just a capital R. The number R is the radius of convergence of the power series. If the series converges only at C, so that's our option number 1, if it does this, then the radius of convergence is R equals 0. Basically, there is no radius if it's just one number. Alright, if it is the set, if it converges for all real numbers, then the radius of convergence is infinity. Okay, then, there, get that to go away. This is just a definition. The set of all values of x for which the power series converges is the interval of convergence of the power series. So those are basically the 2 things that we're going to look at today. Radius of convergence and interval of convergence. Any questions so far? All right, let's look at our 3 examples. Okay. Typical directions: find the interval of convergence and the radius of convergence. They probably won't say be sure to check endpoints, but I have that up here. We need to check endpoints. Really, only this one is the example of the first type, that type number 2 that I was talking to you about. This is the only one that you have to check the endpoints for, which is the second part of the process, which is why it's going to take longer. Because we don't, if it only converges for one number, We don't need to worry about checking endpoints. It's just one number. If it converges for all numbers that are possible, all real numbers, then we don't need to check endpoints for that either. Does that make sense? We just check endpoints when it's an actual, just a limited interval. All right, let's see. Now, one thing is good, and that is to do this, we're going to use one test, the ratio test, period. Just write that down. We're using the ratio test to test convergence. We're not picking and choosing different tests. It is the ratio test, period. Now, when we start checking endpoints, we will have to pull from our knowledge of the last unit and use different tests from the last unit. You know, alternating series, p-series, different kinds of things. We will need to do that. But for the initial, for the test of convergence, it is always, always the ratio test. So let's remind ourselves of the part of the ratio test that we're going to be using quite a bit. So the limit as n approaches infinity, we have a sub n plus 1 over a sub n. And this is the criteria for convergence, if you remember, from the ratio test. If this number turns out to be less than 1, then it converges. So this shows convergence. And that's what we're going for. That's what we're going for. So if you don't remember or just want to note, you should put that there. We're going to use that every time. Okay, so let's start. We're going to use that. We have limit n goes to infinity. I'm going to go ahead and, like I did in the last unit, I'm not going to write it in this form. I'm going to go ahead and, take it out of complex fraction form as I'm writing it. If that troubles you, then please write it like this first and then take it out of complex fraction form. So the a sub n plus 1 term would have been on top. So we have negative 1 to the n plus 1. We have x minus 5 to the n plus 1. We have n plus 1 in the denominator and 2 to the n plus 1. There's our a sub n plus 1 term. Okay, we're going to multiply it by the reciprocal of our original nth term. So I'm just going to go ahead and write it like that. So we're going to multiply it by, so this denominator would actually go to the top, and then the numerator would go to the bottom. Okay, I'm going to pause there for a sec. So, we've done this test before. We've done the ratio test before. This shouldn't be new or different to you. It's just regular. So our next step is to simplify. So let's work on that. All right, limit and goes to infinity. Let's work on, well, these n's, there's no fixing these guys. So there's no simplifying them. N plus 1. So I have the n and the n plus 1. Those won't simplify. So let's work on the 2's. I have a 2 to the n plus 1 in the denominator and a 2 to the n in the numerator. So kind of think going backwards like we were doing in the last unit. This turns into the 2 to the n times 2 to the first. The 2 to the n's cancel, right? And I'm left with a 2 in the denominator. All right, let's work on the negative ones. Basically, I have negative 1 to the n times negative 1 squared. Here I have negative 1 to the n times negative 1 to the first. What happens to those negative 1 to the n's? They're gone, aren't they? They cancel. I have negative 1 squared left in the numerator. That doesn't do anything. I have negative 1 in the denominator. Now, I'm continuing on with that. I certainly recognize that we have absolute value and it is going to disappear. But to be formal to do it exactly correctly, we need to leave it there until we finish simplifying. All right, so we did the 2's, the x's, the x minus 5's. So I have an x minus 5 to the n and an x minus 5 to the 1 and an x minus 5 to the n. I'm left with an x minus 5 to the 1. Let's see, did we miss anything? No, we got them all, didn't we? Now, this next step is where we divert just a little bit from the techniques that we used previously. Just a little bit. What I'm going to do now is I'm going to take out the parts of this limit that the limit does not affect. So let's think about what that means. This limit is n going to infinity. Is it going to affect this x minus 5 term? No, that's an x, not an n. Is this 2 going to be affected by the limit? No. So I'm going to pull the x minus 5 and the 2 outside the limit. You'll see why in just a moment. I'm going to simplify, take out, the absolute value bars from here, take out the negative 1. I'm just going to pretty it up a bit. So we have x minus 5. Now, why do I still have that in absolute value bars? Is there any guarantee that that's not going to be negative? No, I have to keep the absolute value bars on it. So x minus 5 over 2, limit n goes to infinity. This negative 1 will disappear because of the absolute value bars. We're going to take the absolute value negative 1, it's 1. And I'm left with n over n plus 1. Okay, we okay with that? All right, so let's take the limit. The limit is 1. Okay, so basically we have 1 times this guy right here. And we want to meet this criteria. We want our result to be less than 1. This is the result of the work that we're doing. We want to force this to be less than 1. Okay, with me? So we're setting that up. We're finding our interval of convergence. So absolute value x minus 5 over 2. We're forcing it to be less than 1 because of this test, because of our ratio test. Okay? One way that you could remember it is, think about the geometric series test. When did it converge? When the absolute value of r was less than 1, right? So you can kind of think of it in those terms. We should be used to that already, right? Forcing something to converge. That's what's going on, but it's not because of the geometric series test. It's because of this, because the ratio test. That's when we converge when we're less than 1. So we have to remember, rules about absolute value inequalities. I would multiply by 2. And then I would, if you remember, it's a less than or an and, we would split it up. It would be negative 2 less than x minus 5 less than 2. We solve. Add 5 to both sides. Now, we can't decide whether it's or equal to yet. That is what causes stage 2 of this process. Checking the endpoints, that's what that means. When it says check the endpoint, it means check 7 and check 3 and see if it converges there. And I'm going to take you through that process in just a moment. Then we will decide whether there is an extra equal under there or not. Right now we're going to leave it like that. But let's go ahead and take care of radius of convergence. That's not affected by the endpoints, whether they're part of it or not. So we're going from 3 to 7. One thing to double check your work is to make sure that you're centered where you're supposed to be. Where is this series centered? At 5. Is that our center? Yeah, so we're doing good. We're centered at 5. This portion of it right here, or the other side, it doesn't matter. That portion is called the radius of convergence. And so for this particular example, we would say capital R equals 2. And we've answered one of the questions that they've asked. We have answered the radius of convergence question. All right. So in the other ones, in the other two, that's kind of how far you go, and you stop and you're done with the problem. The reason that I was explaining to you that these are a bit, they take a lot more work is because I have to check the endpoints. I have to see if it converges at the endpoints. Now that's a procedure, and I have wonderful students. You guys line up your work for me, very nice. How I'm going to expect to see you test the endpoints is by telling me which one you're doing. So for example, we're going to check endpoints. All right, let's check the 7 first. When x equals 7. Well, what does that mean? That means what I'm going to do is I'm going to take a 7, and I'm going to go back to my series, and I'm going to put a 7 in for x. And I'm going to simplify it. Then I have a series like we did in the last unit, and I do whatever test I need to do on it. The test that you learned in the last unit. Okay, and you did fabulous on the actual test for that last unit, so I'm sure you remember all of those 10 tests. Sure, you're going to be great. So, I put a 7 in here, and what does this end up being? A 2. So, we say, see, 1 to infinity, negative 1 to the n plus 1, and now that is turned into a 2 to the n over n 2 to the n. So I can simplify pretty easily. So what kind of series do I have there? Alternating. Let's use the alternating series test. Okay, so we're alternating, check. What was the second thing? Decreasing in magnitude. Are we decreasing in magnitude? Yes. Decreasing in magnitude, check. What was the third thing? Limit equals 0. Is the limit of the a sub n term equal to 0? You know, that's the part without the alternating part. Yes? Limit goes to 0. Therefore, what? Converges. Therefore, converges by alternating series test. Should bring back memories. That means, yes, you guessed it, I get to go over here and put that there. Put an equal there. That's what testing the endpoints mean. That means it does converge at 7. We just verified that it converges at 7. So that is part of the interval of convergence. Okay, makes sense? All right. Now let's check the 3. So when x equals 3. All right, we go back to our original, put a 3 in there. I get a negative 2, don't I? All right, so n equals 1 to infinity, negative 1 to the n plus 1. Then I have a negative 2 to the n over n2 to the n. I would like to still cancel out that 2 to the n in the numerator, so I'm going to rewrite it. I'm going to rewrite this as negative 1 to the n times 2 to the n. Are we okay with that? Just using an exponent rule. All right, so let's rewrite. Okay, just like on the other one, I get to get rid of the 2 to the n's. Now let's see what happens with that negative 1 stuff. Alright, I have negative 1 to the n plus 1 times negative 1 to the n. Exponent rules allow me to do what? Just add the exponents. So, of course I'm going through all of the steps. Some of you would be able to go, to eliminate some of these steps. Alright, now let's think about that a little bit more. Could I write this as negative 1 to the 2n times negative 1 to the 1? Sure. Alright, but let's just think. Let's put odd and even terms in here. If I put a 1 in here, 1 times 2 is 2. 2 plus 1 is 3. It's going to give me a negative 1. If I put a 2 in here, 2 times 2 is 4. 4 plus 1 is 5. It's going to give me a negative 1. No matter what number I put in there, and I can't, there's no 0, but from 1 on, this is going to turn into a negative 1. So it's not alternating anymore. It's always negative. So I'm going to rewrite this, taking the constant outside. All right. What is this kind of series? It's a p-series, right? A p-series with a p of 1. What happens with a p-series with a p of 1? Diverges. So this has a p of 1. This diverges by p-series. So this doesn't get an equal sign. So this is my interval of convergence. Now I know I did the very hardest one first, the one that takes most of the work. The other two are going to seem quite simple compared to this one. But that is what you have to do if you have a finite, like 3 to 5 or whatever, interval of convergence. You have to check the endpoints. Okay? All right, questions? All right, I need a little bit of room. I'm going to erase this endpoint checking part so that I can get to this problem. All right. Okay, so what test are we going to use to check for convergence? Ratio test every time. We don't have to try to think of what test to use. You will use it every time. So let's do that. So the n plus 1 term is on top. So I have negative 1 to the n plus 1, x to the 2 times n plus 1 plus 1 over 2 to the n plus 1 plus 1 factorial. Now, kind of visualize with me, this little guy right here is in the denominator. And so we want to fix the complex fraction. We're going to turn them upside down. So we're going to multiply by 2 to the n plus 1 factorial over negative 1 to the n x to the 2n plus 1. All right. So that's what we're going to work on simplifying. Now, I had some students earlier today that were a bit confused by the way that I wrote this. They were confused as to why the 2 applied to both of these terms. Okay, maybe everybody in here, I don't know, maybe completely understands. What I do to get the next term is I open up where the n is and I put in an n plus 1. I mean, that's how it works. Everywhere there's an n, I open that spot up and I put in an n plus 1. That's what happened here. So I actually have to distribute 2n plus 2 plus 1. So I'm going to just write this in a different color. This is going to simplify to be 2n plus 3, as is this one down here. This one is going to simplify to be 2n plus 3. Okay, just so that we know. All right, let's work on the simplification piece. All right, for the negative 1s. Negative 1 to the n plus 1 over negative 1 to the n. That's just a negative 1, right? You with me? I know we're skipping a few steps, but we've been doing this for a while. I'm sure you're just fine. Okay, let's work on the x terms. I have x to the 2n plus 3 right here, and I have x to the 2n plus 1. Okay, think about going backwards in exponents. So I have x to the 2n and x to the 2n. Those are going to cancel, aren't they? And I'm going to be left with x cubed over x to the first. What is that going to simplify to? X squared. So I'm going to be left with an x squared here. Is everybody okay with the x's? All right. Let's work on the factorials. So remember when we were simplifying factorials, we had to determine which one was the biggest. That's the one that we're going to break apart. So which one is the biggest? 2n plus 1 factorial or 2n plus 3 factorial? 2n plus 3 factorial. That's the one that I need to expand. So let's expand it. 2n plus 3, 2n plus 2. Then I'd have a 2n plus 1 factorial, and that would cancel with this one. Let's see, did we take care of everything? Yep, it looks like it. Once we're simplified, then we go to that a little bit unusual step where we pull out of the limit the parts that the limit doesn't touch. Okay, the x squared is really the part that it's not going to touch. Now, do we need to keep the absolute value bars on it like we did on here? No. Is there any chance that x squared is going to be negative? No. So we don't need the absolute value bars. We're just going to bring it out, x squared. The negative 1 is, we're going to absolute value it, and it's going to be a 1. So limit n goes to infinity, 1 over 2n plus 3, 2n plus 2. Okay, we take the limit. What is this limit? 0. So I'm going to have x squared times 0. All right, and let's look back at our criteria. What do we need to converge? Less than 1. Okay. Does it matter what x is going to be? It doesn't, does it? Because 0 times a million is still 0. So for what numbers does this converge? All real numbers, everything. Everything. Okay? Because this limit went to 0. Now, if you like memorizing rules, then you might write that down. If the limit goes to 0, the interval of convergence is all real numbers. And the radius of convergence is half of that, right? Half of that would be infinity. No endpoint checking. I'm sorry. I know you guys like that. Sorry. No endpoint checking. All right, we okay? Last one. Again, no surprise, we're going to use the ratio test. Limit n goes to infinity. N plus 1 factorial. X minus 3 to the n plus 1 over n factorial times x minus 3 to the n. There's our rule. So let's simplify. Let's work on the factorials first. So I have n plus 1 factorial over n factorial. What is that going to simplify to? Just to n plus 1, right? And let's work on the x minus 3 terms. I have an x minus 3 to the n in the denominator and x minus 3 to the n plus 1. What's that going to simplify to? X minus 3 in the numerator. Okay. Oh, there shouldn't be. Goodbye. Okay. The next step is what? Take out the x, the part that's not affected by the limit. Do I need to keep the absolute value on that guy? Yes. So here we go. We have x minus 3 limit n goes to infinity of n plus 1. Okay, what does that limit go to? Infinity. I have infinity times x minus 3. Does it matter what x is? Does it matter what I multiply by infinity? No, it's absolute valued, right? I can't sneak a negative in there. It's absolute valued. Whatever I multiply by is going to be positive. And so what does our ratio test say about things larger than 1? Diverges. So this basically diverges for everything except the center, the 3. It's that type 1 that we were looking at. So this one, radius of convergence is 0. And it converges only if x equals 3. Let's talk about that strange phenomenon. Let's look. If I put a 3 in here, what am I going to get? 0. So my series would be 0 plus 0 plus 0 plus 0. You see why it converges? Plus 0, and that's going to be eventually 0. That's why it's the only place it converges. Every other place will diverge. Okay?